Good morning to all. Myself Professor Archana from IIT ISM Dhanbad. We are in course of Introduction to Python and Petroleum Data Analytics. So we have started in the last class Machine Learning Supervised 1, where we have discussed the simple linear regression and multiple linear regression. In today's class, in continuation to the last one, where we do discuss simple linear regression along with multiple linear regression part. Today I am going to first start with the multiple linear regression scikit-learn and then followed by the gradient descent algorithm. So I stopped till here in the last class, where in the simple linear regression we do have a least square method where we are trying to find the best fit line, and we have come across the deriving the equation for M and C, okay, and then we do started multiple linear regression, where I just mentioned in place of y in case of a simple linear regression, y we are mentioning as a beta 1x plus beta 0. So this beta 0 is nothing which we can call it C or intercept, okay. Here beta 1 is again coefficient, okay. So if the same equation we apply for the more than one feature, okay, and when we have the multiple feature, like here I am taking the n feature, okay, so this is the n feature we do have, okay. So x1, x2, x3, like that it will move up to the xn. So we do have the n, we do have a n feature, okay. Okay, for the n feature we can generalize this equation y is equal to mx plus c. We can generalize and we can mention like that y equal to beta 0 start sigma I equal to 1 to n beta I xi. So this is the equation for multiple linear regression. The same thing we can apply using the scikit-learn, and how this, when you do have more than one feature, how this multiple linear regression works, we can see this one. So I am going back to the code window. So I have already written the code, okay. So just we will go through this one, okay. So working with the multiple linear regression, okay, what we have to do here, first we require to import the library, that is the import numpy as a np. So numpy pandas matplotlib.pyplot, and from sklearn model selection we require to import the train test split, and then sklearn.linear model we require to import the linear regression. Once we done with the import part, second what we have to do, we require to get the data. So here I am using for the multilinear regression, I am using the geological data set, okay. So getting the data CSV file and reading that data and putting into the data frame. This is the second thing. Once you see this one, okay, we can run this, the first one. Once we can see this one, okay. So this is the our data, where we do have a 200 rows and 7 column, okay. So in case of a multiple linear regression, what we are doing, we are working on more than one column, okay. So if we will go back to this one, okay, so there I was just working, okay. So just take one blank paper, okay. So here we can take, so this is the one, okay. So this is the line for my, okay, these are the data points, some data point may fall onto this one. So this is what, this is nothing but your simple linear regression, okay, or we can call that ordinary linear equation, okay, where we do have y is equal to mx plus c, okay, we can mention anything c or b, okay. So this is the line, when this the line which is passing from the different data point, and when we call this line as a best fit line, when you do have a cost error function or cost function, or we call error function, is a minimum. So how we are defining this as a minimum? Okay, this error is minimum. So what is the error we are taking? I is equal to 1 to n yi minus yi hat to the whole square by n. So this root mean square error is the minimum. So when this error is minimum, what we are calling this is the best fit line. So what we need, we are just drawing a straight line here. But in case of a multiple linear regression, what we have, okay, we will have a data in the 3 dimension. Okay, so this is the one we are talking about. Okay, and here you will have a plane. Okay, so this is the plane, this is the 3D, because for the simplicity I am just taking 2 feature. Okay, one would be the target and then the 2 will be the input column. So one input and then input, I am just, you may keep 2 or 3. Okay, so for simplification you may keep 2 or output, or you may have a target or label function, label. Okay, so here in case of a multiple linear regression 3D, okay, you will have a plane. Okay, when we go for the higher, like 4 hyperplane, like that we do call. Okay, so this the plane we required in case of a multiple linear regression. We will able to see this one. Okay, so how it works? So here I was. Okay, so you can see it here. Okay, I do have a total 7 column. Okay, you can see here total 7 column you do have. Okay, this is the column we are talking about, 7 column we do have. So once you see df dot column, you can see you do have a porosity, matrix permeability, like that we do have a total 7 column. So one thing we require to do, we require to identify which is the target. So just in this particular example, I am taking a root k as a target. Okay, so y equal to df a root, so this is my y. Talking about the x, so I require to drop all the column which is I am not taking. If I will be taking this all 6 column as a x, I don't want to make that complicated, so it would be multi-dimensional. Okay, and it will be of higher order. So just for the simplicity, what we are doing, just we are taking 2 column, that is a matrix or matrix permeability in the current example. Okay, and then we are taking the other one a root as a target. So if I am taking matrix or matrix permeability only here for x, so this is my x1 and this is going to be x2, and then other column, rest column, I need to drop it. Okay, so when I am taking x is equal to df drop, we are calling drop from the pandas, and then column all the name which you want to feature you wanted to drop, you require to put it as a comma separated and inside the bracket. Okay, so here inside the bracket comma separated we are putting. Okay, so this the x and y we have defined. Now the next what we have to do, from the sklearn dot linear model we are just already imported this the one. Okay, we have imported this the library. Okay, so no issue. Okay, what we are doing it here, we are doing the train test split. So this is the line of the code, it does the train test split. So x and y already we have defined, then we are initializing that one. So lr dot linear regression we did it, then we are doing the fitting for the x train and y train. And once you run this piece of a code, okay, just run this one. Okay, now the next also we have initialized this. Okay, now the next what we have to do, after all this initialization and fitting x train and y train, we wanted to see that our data in the 3-dimensional. Okay, so how we are going to do this one, through the plot we are going to do. Okay, so we require to write the code, and using this we are mentioning here ax dot scatter plot. Through the scatter plot we are checking this. Okay, so this we will start with assigning all the value coding for this scatter plot, and we are giving in x test we are giving porosity in percentage, and x test we are giving matrix permeability. Okay, and then after that we do have this the piece of the code, this all has been written to get this one in the 3-dimensional. Okay, so just once you run this one, okay, this is the one we are able to see. So how it does look. Okay, So this is the plane. Maybe at this point of time we won't be able to understand this code, but once you write it and do this, okay, you will able to see this the one, okay, you are able to see, okay, this is the plane in the, we are able to see in the 3D, okay. So we do have here, we can see matrix permeability, okay, you do have the porosity, okay, and then we do have the A root, okay. So Z label, it is the A root, okay. So this is the one, okay. The same thing, once one more 2 column we can take it. So here again we are taking the 2 column, okay, where we are just dropping all, or what we are considering acoustic impedance and TOC percentage we are taking. Initially 2 column, just we have taken porosity and matrix permeability, and we have seen the, again one more exercise what we can do, we can consider any 2 columns. So here another 2 column has been selected, acoustic impedance and TOC percentage, and once you do the XY, then once you after that you do the trend test split, then we initialize the linear regression, okay, and again write the piece of the code for this plotting multiple linear regression based fit in the 3D, you will able to see this plane. So this is about the using the scikit-learn, how we are doing this one, okay. So now we will go back to the, so now we do see this multiple linear regression, okay, and simple linear regression also we have seen previously, okay. So now moving on to the next. So this the one which we do discuss, that is nothing but the, we do call the ordinary least square. So this the one which we discuss, that is the ordinary least square. So what it is? It is a closed form analytical method to find the exact best fit line in a linear regression. How we are doing that, this one? By minimizing the square residue in a single calculation, okay. So this is the one we do discuss already. Now next which we are going to discuss, that is the one gradient descent. So these two does the same thing, okay. So why we are opting for gradient descent over the OLS, that's the question here which we required to see, okay. So OLS is what? It's a direct mathematical approach to find the optimal coefficient for the linear regression model, which we are finding the coefficient. So how it is working? It minimizes the sum of a square differences between the observed value and the predicted one from the model. So that's the one we do discussed cost function, okay, or error we do have. So that is the sigma of I is equal to 1 to n and yi minus yi hat to square. So yi hat is your predicted value from the model. So till here we are clear. So if we do talk about the strength, so it provides an exact, unbiased and efficient solution in a single step, or making it ideal for a simpler data set with a clear linear relationship, okay. So that's the very important. When do have a simpler data set with the clear linear relationship, this is working very well, okay. And what is the limitation of this one? So ordinary least square can be computationally expensive or prone to overfitting with the large data set or too many feature if we do have, okay. Currently in the multiple linear regression, what we have worked? We have worked with the 2, but there was just 7 feature. So if we do have the more feature, it is going to it may prone to the overfitting, okay, or with the large data set, okay. So now to handle that, we do have one more algorithm, that is a gradient descent. So what is the gradient descent? It is a powerful iterative optimization technique which is used to find the minimum of a function. So what is the minimum of a function? So that's the one cost we are talking about. So this is the one, if we will do take, so this is the, so why I do make this the parabolic structure, that we will come to this one, okay. So this is the cost function, okay. Okay, let me draw the properly, okay. So this is the cost function, okay, and here if we will take p, okay, keeping m constant, okay, that's the one thing. To simplification, what we are making it slope constant, okay. So that's the one. So here where we do see, this is the minimum we do have, okay. So this the minimum, so this is my error or loss, okay. So we can represent L is nothing but the loss, okay, and then B. So we require to find at this particular B what we need. We require the when you will have a minimum loss, okay, when at this B position, we are going to have a minimum loss, because here what we are able to see, this is the at the minimum point. Okay, so this we require to find what is the optimum B. For that, loss function is going to be minimum. Okay, so how does it work? Okay, it takes a repetitive step in a direction opposite to the gradient. Okay, so this the we are talking, this the gradient we are talking. Okay, of it choose it cost function, progressively refining the parameter to reduce error. Okay, so this, how does it work? We will be going to talk about that in detail. So strength, if we do talk about flexibility, it is a highly versatile and can handle complex non-linear model and large data set, where the closed form solution like OLS, that is ordinary least square, is unavailable. So what we do see difference from the previous one, that is limited to the smaller data set and few number of features. Okay, and this one we have the, it is applicable on the nonlinear model and with the large data set. Okay, so scalability is well suited for the massive data set and high dimensional problem that OLS cannot handle. Okay, and then talking about the regularization, it easily integrates with the regularization techniques like lasso. Okay, so talking about the limitation, iterative process, the solution is not found in the single step but required many iteration, which can be time consuming. And then here it comes the concept of a learning rate, which we are going to discuss. So learning rate, the performance is dependent on the learning rate, a parameter that controls the size of the step taken during the optimization. Okay, so when we require to choose OLS and gradient descent, that we are clear. OLS, where to choose this OLS? This is applicable for the smaller data set, and when we do have the linear relationship with the few feature. When we do not have a linear relationship between the feature and our data set is very large and it has a high dimensionality, we require to opt for the gradient descent. Okay, so this the in nutshell what we have. Gradient descent is a fundamental algorithm in machine learning and optimization. It is used for the task like training neural network, fitting regression line, and minimizing the cost function in the model. That's the one we are going to discuss, minimizing cost function in the model. So what is the cost function? We are very clear. So about the cost function from the previous all discussion. So gradient descent is an algorithm and it is used to find the best solution to a problem by making the small adjustment in the right direction. Okay, so this is the one. So let's start the discussion on the gradient descent algorithm. Okay, algorithm. Okay, so what we have talked, so this the one, we do have the line. Okay, if you do take the line, okay. So this is the OLS line. Okay, ordinary least square line. Okay, these are the different data point. Okay, so what we do see it here. Okay, when we do call the best fit line, when you do have a sum of a error. Okay, so the cost function, how we define, or error, cost function or error, how do we define? Okay, sigma of I to the 1 to n yi minus yi hat square. So this the one we do have it. Okay, when this value is minimum, okay, for that we do call, okay, this is the my best fit line. So this yi is what? This is the observed value and yi hat is the predicted value. Okay, so when this the difference between this yi minus yi hat square difference is minimum, that time what we do mention, okay, this the one we do have the best fit line. Okay, so when we do just we will be having the detailing from this one. So we can have yi hat. Okay, what with the equation we do have mxi plus c. Okay, so just take this one. Okay, what we will be seeing, put this equation here. So yi minus mxi plus c to the whole square. Okay, y I equal to 1 to n. Okay, so this is the one we do have. Okay, just assume that, okay, we are having m constant. Okay, so if you do have a m constant, m is nothing but the slope, so we are making it constant. Okay, if you have this m constant, so which parameter you require to work along to make this equating to minimum? Okay, only changes in C required to bring, okay, to make whole expression minimum. Okay, so we can only play around the value, that is a b. Okay, so assume this the one we do have. Okay, so now what is required? C required to be make it with the constant slope. What maximum we can do? We can make the C up and down. Okay, either we can make it here or we can make it here. So in this all, what is there? Your slope is constant, your slope is in all the line, but what is changing? This the value, this is your intercept. This intercept is getting changed. Here assume b1. Okay, so this is b2, b3. At different when we just make this line up and down, okay, keeping the slope constant, only this b value is getting changed, correct? Okay, so go back to this equation again. Okay, when we solve this one, okay, so this the one x and y. Okay, so what is constant here? Here it is a loss function, so just I am putting it by the code L. Okay, so I am keeping it L. So L is what? If these all are constant, so only L is a c square. Okay, so from the simple mathematics, if L is varying with the c only, c square, so how my line will be? Not, it is not equal. Okay, so only L is varying with the c, and that is also in a square. So how my line will be? It will be nothing but it will be as a parabol. Okay, so this the minimum line I have it. I am looking for this line, this the value I am looking for. Okay, so this is your parabolic equation. Okay, so this is my loss function and this is my c. So only what I want, okay, I want to bring, I need to calculate this value, need to calculate this c value. Okay, for this c value, okay, what the loss is the minimum. Okay, so how this c value will be calculated, that's the whole discussion here. So this c value I am going to calculate through the iterative way. So that's the required, how it would be required. Just see this one. When we go for the iteration, initial value we require to take some value. Okay, so assume I am taking, this is the c, initial c I have, don't keep it here. Okay, so I require to make the assumption. Okay, so for each c, what I will have? I will have some, so this is my initial assumption, this is the assumption I am taking. So this is my initial assumption. Okay, for this assumption I will be going up, so this is my slope. Okay, so this is my slope. Okay, I require to reach to this point. Okay, so how we can reach to this point? Okay, so what we can do? Okay, we can go like that slowly, we can reach on this line, or we can just jump here, then here, like that also we can go. There could be, again I can jump here, I can go like that. Okay, so objective is to, I require to reach to the C. C is nothing but the intercept here. I require to reach to the C. Okay, and here how I am making the movement, from here I may jump here, then I may come here. Okay, so this is the couple of the possibility I do have. Now go back to see this the equation. Okay, so what I am going to do, I am going to make the take the differentiation of that one, because how I will be going here. Okay, so just what I am going to do, I am going to take the differentiation with respect to dl by dl. Okay, so when you do this one, okay, well, let's go to the next page. Okay, this is the point, okay, minimum point, this is the point, okay. So let's see. Okay, so what was the equation we do had? We do have L is equal to sigma of I is equal to 1 to n yi mxi plus minus c to the whole square. Okay. Okay, so we had the equation, okay, that is your loss function. We had the equation loss function, okay, loss L equal to sigma of I n, okay, yi minus mxi minus c to the whole square. Okay, so how we are going to solve this one? Okay, so first what we require to do, we require to calculate this one. Okay, to first the simplification what we did it, okay, using the OLS, ordinary least square, we have calculated m value. Okay, that's the one thing. So when we have calculated the m value, what we do see, loss is equal to, like it is a only function of a c square. So we have confirmed this, okay, from the mathematics it will show as your parabolic. Okay, now next what we have to do, we require to solve this one. Okay, so we require to reach here, that is a your b, okay, this side b, this side L we do have, we require to reach here. So initially we have to go through the iteration. So first step, okay, so in gradient descent, okay, first assume the value of b, okay, and the m value, that is a slope, we require to take from OLS, okay, ordinary least square. That's the one thing. Then next we require to assume the value of b. Okay, so when we are assuming the value of b, okay, this is the one we have to reach. Okay, so assume, I have assumed the value of b is a minus 10, here it is somewhere. So I will be going up. Okay, okay, so this is your, you reached to this point, that is your here. So to reach here, what you are going to do, okay, this is the slope. Okay, so assume this slope at this point is something, slope here at this point you do have a minus 40. Okay, so seeing this equation, how we are going to do this one? Okay, so you have, okay, okay, so assume you do have the slope is minus 14. So you have b new is equal to b old minus slope. Okay. So this minus slope, so b old we do have minus 10, and then slope we are having something, we are taking minus 40. Okay, so this the one, minus 10 plus 40, so we do have a 30. Okay, now b value I am getting immediately 30. So 30 somewhere it will come here. Okay, so I have to reach here. Okay, some assume you have the 30 point here. Okay, okay, so now the next new b you have 30. Okay, you require to take this b. Okay, so now the next calculation will be here. Again you require to calculate the slope here. Okay, what is the slope at this point? Assume you have the slope something like assume then 20. Okay, so this side what we do see, talking about the slope. Okay, when we are here minus 10 and reaching to this one slope, so this is my what, this is my negative slope. Okay, so this the one we do have the negative slope. Okay, and then we do have the positive slope. Okay, so when we are going to the okay, so what we do see here, I have taken slope is equal to minus 40. Okay, so that what I am trying to say here, when we do have a negative slope, okay, so I am putting in this one b new equal to b old minus slope. So what we do have, minus 10 minus, and then slope we have taken for minus 40. So whole b new you are getting 30. So when you do have a negative slope, you are increasing the value of b. When assume you are taking one more slope, that is a positive. So I have taken the b is equal to 20 at this position. So when we do have b is equal to 20 at here, we are taking, okay. So now my b old is 30 and minus 20. So we are having the b value is the 10. So what we are doing? B we are reducing. When we do have the negative slope, b we are increasing. When we do have a positive slope, b we are reducing, okay. So to handle this all, okay, positive negative, what is happening here, we can take one example, okay. When it is going, okay, so this iteration will keep going, okay. So it will here, then maybe here, then here, then here. So this is the minimum we are trying to find it out, okay. So sometimes what will happen is we will miss this point. When we move like that, we are making the zigzag movement here, here, then we are going here, here. Maybe sometime, now we reach here, so maybe we will be here. Sometimes we may miss the minimum point. To tackle this, what we have to do? This is the one learning rate we require to introduce, or we have to transform the function. So how we are going to do? This is the one we are working. B new is equal to b old minus slope. So here n we are going to introduce. So n is nothing but your learning rate. Okay, so this learning rate value we will have normally 0.01. Okay, but it may have 0.1, 0.001 also. Okay, so there is a something called learning rate which we are introducing here. So this is my equation which to calculate the new b we are using. B new is equal to b old minus eta slope. So slope is the one which we do have it, okay, from the ordinary least square method, and then learning rate we are introducing. We require to transform these equations. We are introducing the learning rate and it controls this algorithm. So what is the learning rate? It is an important hyperparameter in a gradient descent that controls how big or small the step should be when going downward in gradient for updating the model parameter. So model parameter, what we are doing? B new we are updating by b old minus eta slope. Okay, so that's the one. It is essential to determine how quickly or slowly the algorithm converges towards the minimum of the cost function. We want to reach here, okay, this is my minimum, and for this minimum what I need the value of a, okay, I have put it here, so let it be. So b or c is the same, okay, it is the same intercept only, okay. So what is the optimum learning rate we require to keep? Okay, so shall we keep it too small or shall we keep it too big? So that the question arises. So if learning rate is too small, what will happen? The algorithm will take tiny steps during iteration and converges very slowly. That's the one thing. This can be significantly increases the training time and computational cost, especially for the large data set. If you do have a learning rate is too big, the algorithm may take huge step leading overshooting the minimum of a cost function without settling. Okay, so it will be like that. Here we are taking, just miss the sometime the minimum cost function. Okay, so it failed to converges, causing the algorithm to oscillate. This process is termed as a exploding gradient problem. Okay, so this is the thing I do talk today. Okay, so first we have seen one problem, okay, using scikit-learn, how we work with the multiple linear regression in scikit-learn. Okay, and then second one, we started this talk on gradient descent algorithm. So we try to understand what is this all about, gradient descent algorithm. In the next class, I will be working on the scikit-learn part of the gradient descent algorithm with the example and how it works, that we will see in the next class. Thank you.